Okay, let's go now to a bit more to a situation that's a little bit more complicated, where we have two explanatory variables, not just one, more than one explanatory variables. For example, gender and health condition. So besides the health condition that we saw in the previous videos, now we have also the gender, which means now that we try to explain the expression value as a function of the intercept plus b1 for the health condition plus b2 for the gender condition. So again, we have a basal reference level. For example, let's say that we have two genders here, males and females, and we have two health conditions, healthy and sick. And let's suppose that the reference level that we use is the male health individuals. So you see now that the reference level needs one condition for each one of the two factors. Now, conventionally, let's take the first one, male and health. Okay, so for male health, so this 0 regarding the gender and this 0 regarding the health condition, this equation here will become b0 plus, now this will be 0, so this will cancel out, and this will be 0, so this will go away, so plus 0 plus 0, b0. So the model predicts that for the male health individuals, the value will be this one. Okay. Now, if this is 1 and this is 0, which means that we talk about sick individuals but still males, we will have that. So now we have x equals 0 and g equals 2. No, x equals to 1 and g equals to 0. So this is sick individuals, males. This will be again b0 plus b1, and this will be 0. So this level here will be b0 plus b1. And again, the difference between these two, it will be b0 plus b1 minus b0, it will be b1. Very conventionally, very comfortable for us, because if we estimate b1 being different than 0, it means that being sick, it has some effect on the expression level. Okay, now let's go on. Now if we say that x is 0 and g equals to 1, then we have healthy and females. So healthy females is this one, and this equation will become expression is b0. Now this will be 0 and this will be 1 plus 0 plus b2 equals b0 plus b2. So this level here, it will be b0 plus b2, and comfortably for us this difference will be just b2. Great. And if this is 1 and this 1, then the expression level will be b0 plus b1 plus b2, because this will be 1 and this will be 1. So x will be 1 and g will be 1. And this is now sick female individuals. Sick female individuals, it means that we are up to here, and this will be B0 plus B1 plus B2. So compared to the healthy females, so the healthy females are here, they are B0 plus B2. The sick females are B0 plus B1 plus B2 minus B0 minus B2. So let's write it here to understand it. It will be B0 plus B1 plus B2, this level up here, minus this level here, which is B0 plus B2. Now if we remove this parenthesis, it will be B0 plus B1 plus B2 minus B0 minus B2. So this cancels out with these guys and remains just B1. So this difference from here to here is B1. And notice that this B1 is exactly the same like this B1, which means that the effect of sickness, being sick, is exactly the same in both genders. So the effect of the health condition is the same for both genders. This means that there is no interaction between the X and the G variable here. Okay. I hope that this is clear. Please take a minute to think about it. It's very clear with the equations here. In words, it means that being sick, it has the same effect on the expression levels, regardless being a male or a female. And you can see that very clearly with the equations. Okay. Let's go now to R to see a simple example of that. And another thing that I must mention, because we will see that in R, here we have two variables, gender and health condition. Often we are interested in the effect of one of them. So what is the effect of health condition on the expression level, given that we have in our sample both males and females? In this case, it is advised to use also the gender variable in the equation. And we will see now how to calculate the health, the coefficients for the health condition. So here the B1. Because the B1 is the effect of health condition on the expression level. We see it here and here. The same effect as we said previously. Okay. So when we have data that we have healthy and sick people and males and females, it is advised always to use both of them in the equation. So to have two variables. If, however, you will use just one, we will see the effect on the statistical evaluation of the parameters in the example of the R here, by doing the example. Okay, so now let's suppose that we have 8 healthy individuals and 8 sick individuals. The expression values of these healthy individuals are these 8 values here. I just separated them just to notice that these are males and these are females, and for the sick individuals these are males and these are females. So by just looking at the values, we see that healthy individuals are lower regarding the expression values on the sick. So you see the values here 2.4, 7.3, 3.1, 6.4, 7.4, and so on. And here we have something like 21, 22, 16, 8, 25, 24, 23, 24. And we also see that the females have higher expression values than the male individuals here. Okay, anyway, let's go. So healthy, sick, the expression value is the concatenation between healthy and sick. So these are the expression values that we have, 8 plus 8, 16 expression values. The first 8 are healthy, the last 8 are sick, the first 4 are males, then we have 4 females, then we have 4 males, and then 4 females, because we concatenate like that. So 4 males, 4 females, 4 males, 4 females. The condition is a factor of 8 and 8 values, 8 healthy, 8 sick, and the gender is a factor of 4, 4, 4, 4 values, 4 males, 4 females, 4 males, 4 females. Okay, here. Now, let's keep that on the side for a moment. So the model, by assuming that we don't have any interaction between the condition and the gender, is written like that. That the expression value is a function, we use a tilde here, of the condition plus, so the important thing is the plus here, the gender. When we will have interaction, we will use this operator. But now that we don't have any interaction, we use the plus operator. Okay, so the expression value is modeled like that. And if we do the summary of this model, we see the following result. The intercept is 2.706. If we go here, the intercept is this B0, and it's the average value of the male healthy individuals. So it's the average value of these 4 values here. If I find the average of these values, just to demonstrate that, mean of these values is 3.7. What did we have here? 2.7. Let's see why this is happening. Okay, now let me explain this observation here. So we have this healthy and sick, and we saw that for the healthy individuals, for the healthy males, so these 4 values here, the mean is 3.7. However, the model predicts here that the intercept term is 2.706, which is not exactly the same like the mean value of the male healthy guys. Now, this is because in this simple model here, we don't assume any interaction between these 2 terms here. So the effect of the gender is the same for both conditions, and the effect of the health and sick condition is the same for both genders. In order to achieve this no interaction thing here, it is possible that the model has to shift a bit the estimates, because it has to fit the requirement that there is no interaction between these 2 guys. So for example, in order to make this a bit more clear, even though it's not so important for the class, now if these are the male healthy and these are the female healthy, and these are the male healthy and male sick, and these are the female sick, so you see that the increase in the expression level for the females is very big, but the increase for the male is not so big. smaller. If we don't put any interaction terms, so we say that gender and health do not interact with each other, it means that the effect of being sick is the same for both genders, according to the model. Which means, if we want to visualize it, that if we have such an increase here, then we must have a parallel increase here, same one, because this must be the same with this. Obviously this is not a good fit, so what R will try to do will probably to find a compensation between these. So maybe something like that here, and I don't know, something like that here, to find a good compensation between fitting these values and these values with these lines. And the prediction then for these guys will be this one, whereas the mean value will be a bit lower. The prediction for these guys will be this one, so this will be 0 here, but the mean value is a bit higher here. Okay, let's go back to our data. What I want to stress here is that when we have more than one variable, 2 variables, for example, like here, the estimates do not necessarily represent mean values. They represent mean values if really, truly, there is no interaction between these two variables. Since I use some whatever random values here, perhaps the best model is a model with some interaction, and that's why these estimates do not really represent the mean values of the classes. Anyway, let's go on. So when we use these two variables and we fit the model, we see the following, that the intercept is 2.7. Being sick, regardless the gender, it has a plus 15.16 compared to the intercept. So being sick means that regardless your gender, if you are male or female, you have an increase, which is this B1 here, plus 15 point something. And being a female, also, regardless the being sick or not, it has an effect of plus 5.4. Now, both of these values, especially this condition sick, is statistically significant. 8.57 multiplied by 10 to the minus 7 and 0.008 respectively. Okay, now using this modeling of 2 variables, we saw that being sick, it has a strong effect on your expression levels. Now let's suppose that we neglect the 2 variables and we model the expression by just using the condition. We neglect the gender. What will be the effect of neglecting the gender? Now, again, I remind you that these are the values here. And in this case, being sick, so the intercept is 5.4. The 5.4 actually is the mean value of the healthy people, so it's somewhere here, regardless the gender. And being sick it has a plus 15.16, so up to here this difference is 15.16 and statistically significant. Okay, then you might wonder, okay, why to use the gender, since if we don't use the gender, still we find that the effect of being sick is statistically significant. Now, imagine the following example, that these values are not like that, but being a female here, it has a much stronger effect. So let's say that this is, it's not 6 but 36, it's not 7 but 37, this is 38 and this is 36, and here is not 20 but it's 50, 5, 54. So I just used a strong effect being female, so plus 30 compared to what it was. Now graphically this is like that. So these are the males, and before the males, the females were here, but now they will not be here, they will be up here. And so these are the females, these are the males, healthy individuals. And yeah, let's see the values for the other part. So this will be 20 somewhere here. And these are male sick, and female sick will be up here. Now clearly being sick has an effect on the expression levels. You see that you get an increase from here to here for males and from here to here for the females. But the variance within each condition is huge. So you see the range of the values for males here, down here, and for females up here. For males down here and for females up here. The variance is so large that perhaps these two mean values are not statistically different if we don't take into account the gender. If we take into account if we don't take into account the gender, we will just try to check whether these values are different. If we take into account the gender, we will see if these values and these values are different. And the variance is much smaller here and much smaller here, so perhaps this difference will be statistically significant. It will be in both cases B1. Whether in this case, since the variance is so large between these two means, this difference will not be statistically different. Okay, let's see. So if we don't take into account the gender, the intercept is 20.425. This is here, 20.245. And being sick, the effect is plus 15.16. So this is plus 15.16. So this will be something like 35 point something. And this difference is not statistically significant, because these variances of these points around the mean is huge. They are very far away from the mean. So if they are so far away from the mean that we cannot say that this difference is large enough. Now if we take into account the gender, then we have the following result. The intercept is 2.7. So the B0 is 2.7. Again, we say that it's not exactly the mean here. It's a bit probably below the mean. Being sick is 15.16 compared to that. So this B1 is 15.16. This is 15.16. Being a female is plus 35. So being a female in both cases is this one, and in both cases plus 35 point something. And now both this and this is highly statistically significant. the p-value is 8.57 and this is 2.9 multiplied by the 10 to the minus 11 multiplied by the 10 to the minus 7 here. So when we take into account the gender, we see that the effect of being sick is statistically significant. If we don't take it into account the gender, we cannot demonstrate the significance of being sick or not. And again, we don't have any interaction here, so the model is forced to have this effect exactly the same for females and the males. Okay, so this was this video. Thank you so much.